Thank you for joining us. I'm delighted to welcome to the forum Luc Brandts, the CEO of the Software Improvement Group, and Jasper, the Director of Consulting for Software Improvement Group, who are going to talk to us about why software quality monitoring can be fundamentally flawed and how to get it right. Luc, over to you.
Thank you, Justin. So today, indeed, we're going to speak about quality monitoring and looking at all the other sessions we saw earlier today and yesterday. We see there's a strong need for what we think is a good addition to these stories. But before we get there, let me quickly introduce ourselves. Jasper will go into more detail. He's the director of our US consulting services out of New York. And I'm the CEO of the Software Improvement Group. I have a background in governance, risk and compliance. I've been working in financial services industry for a long time, and we sold our company to NASDAQ a couple of years ago. Also had the pleasure to work in that industry for a couple of years. So quite familiar with all the rules and regulations that play in that field. And with that background, I think it's good to maybe discuss a little bit about what quality assurance can be looked at. So if we move to the next slide, I'd first like to introduce the Software Improvement Group to you, because obviously there might be a bunch among you who haven't heard of us before. Although we were founded back in 2000, we have offices in New York. Again, that's where Jasper is operating out of our Amsterdam head office, Copenhagen, Antwerp, and Stuttgart. And we serve a large number of clients across industries, but obviously financial services is well represented there. We probably have the world's largest software quality benchmark database with over 36 billion lines of code in over 300 different technologies, which gives us a unique perspective on the market with thousands of systems and active monitoring. So with that very brief background on who we are as a company, where we provide both technology as well as the corresponding services, I'd like to present two different approaches to software assurance, where we feel both are really required. There's the outside-in approach, where mostly we look at the external quality. We've seen many examples of those earlier today, where the focus of most QA teams is about the functional suitability. Are the user stories correctly implemented? Are we complying with rules and regulations? Is the software correct? And can it be accepted into production? And that's, of course, of utmost importance. I don't want to dismiss this in any way, but we do want to stress the fact that you also need to look at the other side of this story, which is what we like to call build quality or internal quality, more like an inside out based on code analysis. Because the build quality in the end of the day drives the cost of ownership and external quality. And Jasper will be able to provide you some great examples there. But before we move there, I'd like to tell you why internal quality matters so much. When we use our benchmark, ranging from the worst possible systems with 1 star to the best possible systems at 5 stars through the industry average that we've set at 3 stars, we can see that 60% of all bugs is directly attributable to build code quality. But when we compare those stars, and when you operate at a 4-star level, you can see that your development speeds will be 3.5 to 4 times faster than in a 2-star system, and even up to 10 times faster when you're comparing a 5-star system to 1 star. Your cost of ownership is going to be 2 times lower comparing 4 to 2 stars, and so on. So that means that the build quality is of very, very strong of relevance. It's not something to easily dismiss. Having said that, this doesn't mean that you always have to operate at the utmost highest level of quality. It's when you buy a car, it's not necessary to always buy at a Rolls-Royce level for several reasons, by the way. But so when you look at maybe the next slide, the build quality, there is that balance that you need to find. Do you want to have this system that's maybe very bad? In car terms, it's rusting in the brochure, or does it need to be at this Rolls-Royce flawless level where you understand that might be costing a little bit more to build? Well, that depends. You need to have this trade-off that you need to make. You need to look at your your business requirements to see where you need to be. If you have an application that you maybe are depending on heavily, that you need to integrate with another system that you've acquired from another company, that you need to build a lot of new capabilities into, then in that case, you might have to operate at 4 stars or even more. However, on the other side, if you have a system that's maybe 20 years old, that is already quite stable, you're not adding any new functionality, you know you're going to replace it in a couple of years, then in that case, you might say, well, I can live with a lot lower quality. It depends on the situation. And it's this balancing act that you need to think through. It's not that always you need the utmost in build quality. You need to balance the act, and that needs to be done on risk-based thinking. And when you think about risk-based thinking, that needs to be based on some proper guidelines, some proper methodology. And what are the better methodologies out there than the ISO 31000 standard, where we see here an example. It's a hideously complex structure where there's monitoring review that needs to be done to ensure that risk management is continuous and continuously emerging. There's recording and reporting, that everything is documented properly, that it can be audited. There's the communication and consultation. There's all these elements aside to that. But when you bear down to the essence, you'll see that the risk assessment consists of 3 significant steps. So when we just focus on that part, we see that firstly, there is risk identification, which means you first have to understand all of your risk. You have to know them all. Then you need to analyze them so you really get to grips with them. That's the risk analysis step. And then thirdly, there's this risk evaluation where you evaluate the risk in their context, typically the business context, to understand what you need to do and move to your risk treatment. So it's these 3 steps that you always take. And in most cases, you maybe take them intuitively or in the back of your minds, but you always do this in 3 steps: risk identification, risk analysis, and risk evaluation. So when we put this into a methodology that's closer to our hearts of software assurance, then we see that we have 2 sides. There's the code, the people in the process, the IT side of things, where we first of all identify the risks that are present in that code. Then we analyze it. You have to understand them. You have to base that on models that are scientifically proven, that maybe are relying on a thorough benchmark. And then you need to evaluate them in the business context. As I said, determining which build quality you need depends on what you want to do with this application. And then you will have a double loop continuous improvement aligning business and IT automatically. So this is a fundamental structure where we think everybody should be working against when thinking about this build quality element. However, what do we see in practice? When we look at the common practice that we find every day, it's mostly we look at the code. There's all sorts of code scanners, and don't get me wrong, we don't want you to get rid of those code scanners. They do tremendously good stuff. They find all the vulnerabilities you have in your code, all the issues, all the violations against rules, but then you need to analyze them. You need to analyze them properly and determine, based on the benchmark, what you need to be doing, rather than just have people by themselves and putting some filters into those tools, because then you don't get an indisputable result. You'll get results that's maybe the personal preference, or maybe on somebody's career ideas and based on some thoughts, but then still there's no alignment between the business and IT. There's no analysis that has been done in a formalized way. And then the evaluation is typically also very often combined into this analysis, rather than being something where you explicitly include that business context. So what you'll see is that business and IT are not aligned or not enforced. It's not repeatable. Every project will be done in a different way, and therefore you might be making the wrong decisions. So with that in mind, let's look at a few examples, and I'm handing over to Jasper, who will first introduce himself, to give you some ideas on how you could apply this in practice.
Yeah, thank you, Luc. I'm Jasper Geurts. I'm here in New York, and I've been working for the Software Improvement Group for 6 years now. And 5 of those years I actually primarily focused on financial services industry in the US. So I've had the pleasure of working with a lot of very smart people in large financial institutes here, like banks and insurance firms, to do risk analysis based on this source code analysis that Luke just discussed. So with it said, when we look at how systems are implemented, this is a nice overview of how a very complex functionality, so a complex algorithm for automated trading as an example, how that can be implemented. And this picture that requires a little bit of context. So what you see is these individual units, these individual blocks. So they represent a piece of code, a code that a developer has written. So all of that code together build up this system. So the height of this block represents the amount of code that is inside of a unit. And a unit of code can be a method in Java, for instance, or a rule in Pega, or a program in COBOL. So it is the smallest executable part of the code base, which can be tested individually. So the color here is very interesting. The color means the complexity of the code. And with complexity, we mean if-else statements. So cyclomatic complexity, for instance, is something that developers need to be doing in order to build the functionality. So this might be a similar system. From a functional perspective, it might do the exact same thing. It's only engineered in a different way. It's engineered in a complex way. So you see that the units are way bigger than the other system, and that it actually has a lot more complexity. So why does that matter for risk analysis and risk assessment? I actually want to make a comparison there with how we advance in technology. So as technology innovation grows, we get a lot more better tools, and tools that are very interesting, things that become commodity, that allows us to create code very quickly. But it also allows us to make things very complex. And when you look at human nature and our cognitive capabilities, in the past 10,000 years, those didn't really change that much. So still a human being is challenged with all kinds of problems. So 10,000 years, there were different problems than now. But the idea here is that ultimately it's still a human being that needs to understand the code and all of that complexity that comes with it. So this is where SIG, or we introduce the idea of technical debt that can be part of a software system. So what does that actually mean? So it is that basically the cost of repairing craft. And craft is badly designed code, or unnecessarily complex code, or unwanted code, things that can be introduced because teams needed, or individual developers needed to make decisions. Maybe they needed to do stuff very quickly. Maybe there's some other reasons. But ultimately, what you saw in that picture, if things become very, very big, in terms of the complexity and the technical depth that is inside of a code base, it becomes very hard to change it, because it becomes very hard to understand it. So without repairing that, you're actually paying interest exponentially. And this means that you need to spend more time on understanding a piece of code, you need to spend more time on fixing bugs, and you need to spend more time on repairing maintenance defects. And there are actually different ways on how companies handle this, which is observed by us, but also Martin Fowler created this nice diagram of that. So there are teams that are cautious, there are teams that are reckless. There are teams that do intentional technical debt and unintentional. So these are two very different types of ways on how to handle technical debt. So if you're cautious and intentional, it means that you understand the risk of introducing debt, meaning that you are okay with handling with the consequences later. On the other end of the spectrum, so ignorance means it can be startups, right? So we want to ship fast. Copy paste was invented for a reason. YOLO, let's do it. Let's go fast. But ultimately, technical debt can become a problem. So Luke introduced this risk model, right? So, and this is the way that SRG looks at this. So risk identification is very, very key. And we have an ISO 25010 certified model that can look at that. But these are concepts. These are things that you can measure in code, but they actually reflect what a developer needs to do when they want to make very good and maintainable code. So you can measure these things. That is the first step. We first need to understand whether there are actually risks. So how big is it? How much duplication is inside of this code base? How complex is it built? How do different modules and components communicate with one another? This is a very important step in risk assessment. But then actually you need to put this into perspective, because the idea is this actually a problem for you, your organization, for the developers? And the way that we do it is we benchmark that against these billions of lines of code in very a lot of different technologies that we've seen before, to understand where the current market is operating. the idea behind this is that if you have a piece of code that needs to be changed in the future, and there's a big chance that it needs to be changed in the future, you need to have somebody that understands that code, even if that person doesn't work in the organization anymore. So therefore, we look at the market, the software industry market, in which direction is it heading? And we do that by measuring a lot of code, a lot of actual implemented code. And then it comes into this next phase, which is the risk evaluation phase. It might be that there's lots of technical debt that is there because it was designed. So you can imagine, for instance, a architecture style where all services are independently developed from one another, so that you can deploy them and test them in isolation, which is great. But what we oftentimes see is that there's a lot of duplication between these individual services. So duplication per se is not a good practice, because you want to build things once and just reutilize that throughout your system. But in this sense, it makes sense to have duplication, because that means that you don't have to have common code. That is going to be a lot of communication lines between all of these services. So it might score low on this model, but it doesn't necessarily mean that it is a problem. And this evaluation is very, very important when you do risk assessment. So sometimes we come across situations where the amount of technical debt is just too high. And then you come to situations where people, very important people, ask, how the heck did we get there? And this is actually a quote from New Jersey Governor Phil Murphy during the COVID-19 press conference a couple of months ago, where there were actually a lot of unemployment claims problems, because that increased with 16,000%, which is a lot. And we don't know, so we haven't seen those systems, but it is essentially a question on how do we still run on these 40-plus-year-old systems? A problem or a challenge that lots of banks and all kinds of different organizations are struggling with. So with this idea of risk management in mind, we also work in these types of projects where we help out organizations to go from a situation when there's a lot of legacy code, a lot of monolithical designed systems, where sometimes hundreds of people are working on daily, but these things are very, very interconnected, very coupled also with the database. It are essentially very complex systems. And what we want to do, we want to move to this target situation where everything is loosely coupled, where we can deploy things individually, where we can test it better, etc. But obviously there's lots of different problems here, lots of risks that are actually really core to the product itself. So the main challenges that we observe in the market is that there's a need for incremental modernization. So you can't just wait for 3 or 5 years until you got this big monolith out of the way and have your beautiful new architecture there. Obviously, this needs to be in increments. You want to do the important things first and then the less important things last. Another big problem here is that those systems are very, very big. There are millions of lines of code. These things are also very old, very complicated. Across the many years that they've been developed, they build up a lot of complexity there. Third point here is that knowledge is very thinly distributed. So sometimes these systems, or oftentimes these systems, are built with technologies that are not being taught on the universities anymore. Languages like COBOL. This is why Phil Murphy asked for COBOL developers, because the knowledge isn't inside of the organization anymore. Sometimes even when I do these kind of assessments on these systems, we discover code that hasn't been touched for 10 years. That's great because it's very stable code apparently, but if you need to change it because you're in this modernization phase, you need to understand it to break it apart. And here again comes in the risk assessment. So we need to first and foremost do identification. So what is it what we actually have in those legacy systems? And this is again a graphical representation of what a implemented architecture can look like. So we as the software improvement group, we've built these different models on these ISO standards to do that in a very independent way. So we look at how is this actually built? How is this implemented? And you can go very deep there when you are arguing about, for instance, architecture quality. So how are the different components communicating with one another? How are they constructed inside of it? But also what kind of technologies are actually used. And when you go back in time, how often are these things changed? So how active is the knowledge of the people that are actually working on these things? So this is identification, just knowing the facts. Then you go into your risk analysis, again, where we use benchmarking. So what do we normally see, typically see in these types of organizations and these type of software systems to kind of understand whether this is a good or bad practice or a risk for the breakdown of such a component. So you can see a couple of things here. So these are strutcom, det, etc. So what this basically means is the structure of the system, the structure of this component, the communication within and between components, the entanglement with the database, the technology stack that is used, the evolution of that technology, and the knowledge that people still have. Those are very important concepts when you think about moving or migrating away from a certain architecture to another one. This is where risk analysis comes in. But then, of course, you have risk evaluation. So there you need to think about what actually makes sense for us as an organization, pulling in the business context. In this sense, we can kind of predict what the different mitigation scenarios are in terms of the risks. So when you look at this particular component that I highlighted here, you can see that apparently the knowledge in the technology stack is score low. So this is dated technology, something that we don't want, but the actual structure is still okay. And it's not very much entangled with the database. So that should be okay if we just re-platform that into a different technology rather than rebuilding the whole thing at once. Right, so these are a couple of ideas and a couple of examples from the practice that we are in when SIG enables this model and the way that we look at code in these kind of risk assessment situations, but also when we, for instance, go into an IT due diligence. When a bank wants to acquire a smaller fintech, we want to understand what are the risks of the code that has been built there, and will it actually integrate nicely into what we already have? So using this as a risk assessment model from the ISO 31000 really gives us the opportunity to talk about this and advise our clients in this. And with that, actually, I want to give it the word back to Luc for some final.
Yeah, thank you, Jasper. A great summary as always. So things you can do tomorrow is, first of all, realize that assessing risk is always done in 3 steps. You always identify, then you always analyze, and then you always evaluate. That is something that is just the way risk assessments work. The reality is that most tooling is focusing on the risk identification rather than the analysis and evaluation. So what you should be doing, in our view, is to look at the way you do this today and see how this can be further formalized. And look at the way your team does the risk analysis and what choices are being made implicitly and explicitly. And look at the way your team does risk evaluation. How do they take the business objectives into account? Or is this just based on some general, more IT-focused rules? And after you've done that, we feel it's of utmost important to bring the benchmarks into your risk analysis, formalize your risk analysis with adequate tooling. And obviously, we'll be more than willing to provide those to you and to provide you with the advice. And then implement continuous monitoring to formalize that way of working. And maybe to answer the question that just came in, because that ties directly into this story, is how do you see software risk being treated by financial firms at the C-level, and how do our metrics help with that? Well, it's exactly this story where the C-level needs to have an understanding of the key risk of that, what we feel build quality. If the build quality is low, and Jasper just showed what can happen with these 2 clear pictures, one being hyper complex, the other not so complex, we help C-level to look into the code. Software is very often seen as a black box that's very difficult, very complex, and just for IT people, but we help them to quantify the problems in that. And with that, we streamline discussions about technical debt. We often see that developers are shouting, there's too much technical debt, we should be investing more in getting rid of it. And then still management said, well, okay, I can maybe understand what you're saying, but well, can you quantify? Yes, you can quantify. You can actually do this. So what we help doing is this very important concept of internal build quality can be quantified and be presented at a C-level to make everybody understand where your key risks are in your business. So that was a first question, but maybe there are other questions coming in.
There are indeed. We've got quite a lot of questions. That was very interesting. Thank you, Luc, and thank you, Jasper. You mentioned earlier, I think it was Jasper, that you mentioned the challenge of managing technical debt. And I would say I would nuance that and say legacy debt as well, because you also implicitly refer to that. If we're distinguishing technical debt, the stuff that is often the shortcuts that get stuff out the door, and legacy debt, you said you've come across code that's 10 years old. I was working with a bank who had a key, absolutely key component that was completely reliable, that was written in the 80s, and there was long since no one who knew how to change it, and it was never the right decision to replace it. How do you quantify the cost of technical debt and legacy debt, as I've called it? How do you put a hard dollar value on it?
Right. So that's a very, very interesting and good question. The way that we approach it is, so you have this idea of things that are not ideal, something that you should not have if you want to make speed, right? So because we go very deep into the code itself, we know how it is constructed. And of course, we work with these benchmarks because we have a lot of data. This also means that we know what the average productivity of different developers are, so different programmers inside of these different technologies that are out there. Knowing that, you can actually make a calculation. You can think about how much time would it take to get rid of this debt. First, of course, you need to do what we just presented here, a risk assessment, to understand, do we actually need to get rid of everything? What are the things that we first need to solve, and what are the things that we then need to resolve? But the way that we approach that is developer years of investment that you need to do, which is clearly very much connected to actual work that needs to get in to get rid of the debt. And this can be multiplied by average cost of these developers and the supporting teams, right? And this is how you get to a dollar amount. And this is, again, this is very much focused on what you can see inside out. So we really focus on implementation and the code quality. Obviously, there are lots of things that are very important, especially when you want to kind of renew a platform like you just mentioned, where all your regression, everything, all the testing that comes with it. But we've talked a lot about this during this whole kind of QA financial 2 days. Those are very important things. This is not something that we can calculate. What we can calculate, and the way that we can help, is really looking at what are the things that needs to be solved and how much time does it take on average. And this is how we get to a very concrete answer to that question.
Thank you. As you know, I've been working on some benchmarks around what I think you would characterize, and I think it's a very helpful characterization, as external quality. So defect ratios, project overrun, amount of spent on amount of time and effort spent on remediation versus development, and so on and so forth. And you focus on internal measures of code quality, of reliability, and so on and so forth. Can you give a few more examples of things that you consider internal versus external measures, and also how you link those two stories? Because they clearly do need to be linked. The external measures in the end are going to be customer satisfaction and customer revenue. That's the external, but the internal is what's going to drive the external. So can you give some concrete examples and how the two link together?
Jasper, you want to take this?
Yeah, sure. So the first question is, what is inside of that internal quality? So there are actually many different things. So SOG takes the approach of the ISO 25010, which is a standardized framework to look at software product quality. And there are lots of things in there. So what we now covered is basically the maintainability of the code, which is connected to what you're mentioning in your second question, which I'll come back to in a little bit. So inside of that ISO 25010 standard, there are 8 characteristics. Functional suitability being one of them, being very important, obviously, but there's also security, there's privacy, there's performance, reliability, there's all kinds of things that you can actually measure in code that all adds up to this idea of how things are actually built and not how things are actually operating. So we have other models for that, obviously. So how that connects to, so that is the idea behind this maintainability model that we have. Like, how does it connect to the real world, solving bugs, having these issues? Well, as a lot of the models of ours are kind of backed by scientific research, and we have lots of publications on that. So obviously it would be interesting if you go to the website just to check that out. But this predicts, so the build quality predicts the amount of bugs that you have. It also predicts the time that you need to solve it. So those worlds are actually very much interconnected, because the one, and this is the idea again about, it is a human being, it is a person that needs to change code. So whenever there's a bug, there's a person that needs to solve that bug, up until the point where the AI gets so smart that they can do it themselves, or whatever, when they test the, pass the Turing test or the negative Turing test or whatever test there is to solve the AI problem there. But up until that point, we will have human beings that need to understand the code, and therefore those two worlds are very much interconnected.
Thank you. I've just got one final question before we wrap up. You're talking about, for many of you, I think, taking a slightly different approach, a risk-based approach to a combination of issues. Is that likely to result in retooling, either retooling the QA tools specifically or retooling on the development and the development management tools that people use?
Well, that's a good question. I think there was also a similar question already that I tried to quickly answer. It's not that we want you to get rid of tools. You just need to realize that the tools mostly just do the risk identification. You need to have something that puts it into perspective, that analyzes it properly and makes the results usable in that context. So we do feel that some of the tools are very, very useful, but some other tools, well, what's the use of having 10,000 violation of rules and then just sorting them in one particular way or another in the time that you get from somebody who you cannot explain why you would be doing this amount of time. It continues to be a negotiation between people who you can't explain and you can't defend. So you need to structure that approach. So we feel tooling is great, not something to get rid of, but needs to be strengthened in order to put it into a proper alignment with business and IT objectives. That's what we feel, and we've seen working many, many times very successfully.
Luc and Jasper, thank you so much. And I thank you so much for your contribution. I just have a few final words. It's been a tremendous first digital forum for QA Financial. We're very proud to have offered this digital forum as our very practical response to the new world in which we find ourselves. I want to thank all of our sponsors, Applause, Delphix, DQ, Quali, SIG, Sixentix, and Tricentis, without whose support this wouldn't have been possible. And we look forward to our next digital event very soon. Thank you, everyone.